Okay, calculating confidence intervals for proportions. So we continuing on. We've got a value obtained from a population parameter. A value obtained from a population is a parameter, and a value obtained from a sample is a stat. We've seen that before, and we're using statistics as estimates of parameters for a whole population, or sometimes probabilities. Done that too. We make inferences about the populations from what we know about the samples, and indeed we've explained that and been through that. And the new stuff is here. We're looking at two types of estimates. We're looking at point estimates and mainly the second one, interval estimates. Okay. Now a point estimate of P, the population parameter, we use the value of one sample to estimate the sample proportion, to estimate the population proportion. Okay, and that's a single valued estimate, and they're fairly simple, but they're a bit risky sometimes too. The reason why is that if you have this situation here, select a random sample of 20 Australian school kids and find out how much they use social media, what proportion regularly use social media. Let's say it comes out as 0.7, p hat's 0.7. That basically is what we make inferences about for the whole population. Trouble with that, the risk comes in the fact that it might be okay, but it varies from sample to sample. Okay, and we've seen that p hat indeed is a random variable. So what do we do? Well, we can look at what's called an interval estimate. Now, it's an interval that where we're reasonably sure the true population parameter is somewhere in there. We're reasonably sure it contains a parameter, the parameter of the population. Okay, so it's an interval. It's not a single point value. It's an interval. So an interval estimate for the population proportion P is actually called the confidence interval for P. An interval derived from the sample in some declared way. That means there's different types of confidence intervals, which we'll look at in a moment. It's likely to contain the parameter, the true value for the population. So it's not a point, it's an interval. An example of an interval estimate for P is a confidence interval, and that's the one we're looking at. A confidence interval centered on the sample proportion. Now in the previous video we looked at what we can see here, and we derived an expression and we multiplied through. So if you want to go back to that in more detail, see the previous video. And then if we multiply through and simplify as much as possible, we get this expression here. Okay, and we can formalize that into a confidence interval formula, if you like. And that's it here, which you may find on certain formula sheets. Okay, so the approximate confidence interval for sample proportion is given by that. Now notice it actually has two parts separated by a comma, and that will give you the lower end of the interval, and this will give you the upper end of the interval. All right, and the values are P, which is the population proportion, which is unknown, and that's what we're trying to find out about and infer about. But we do know in these situations what P hat is a sample proportion, and N is the sample from which, the size of the sample, okay, sample size from which we took P hat from. Okay, and Z we saw is from the standard normality of it, and Z is a quantile that we've seen before. All right, and so that's how we do it. You just got to be careful how we use it. I'm going to break it down for you in a minute. Note that you probably had a look at these things up here. The examples in this video are going to look at the 95% confidence interval, which has z-scores of 1.96 either side of the mean. But there are two other commonly used ones. I suggest you memorize these. I don't ask you to memorize too much stuff, but I think it's handy to memorize those. Okay, so 95% is, we've said before, it's within 2 standard deviations. Well, there you go, 1.96 is close to 2 of the mean. Okay, and 90% means we're less confident. Okay, 99% more confident, but notice how as we get more confident we have a broader interval. Okay, so and there's my terrible graph. Oh dear, that's unforgivably bad. It's supposed to be symmetrical, you know that. So if that's the mean, which it doesn't look like the mean, does it? If you have a 90%, it may be here. To be 95%, you need to go out further, and then 99% you need to go out further, and it contains a lot more of the area under the curve, which we've seen in the past. So that's the downside. The upside is you're more confident, but the interval's wider too. Okay, more about that in the next video where we interpret this. Okay, we're not into interpreting it in this video. We're into calculating it and understanding the basics of it. So make sure you have noted these 3 points here on the screen at the moment. Now please note that we need n times p and n times 1 minus p, the complement. They need to be greater than 5, as we've seen as per the binomial distribution, the normal approximation of the binomial distribution. Okay, that is also explains the well, it basically works out whether we're eligible to actually use this or not. Okay, so np or n times 1 minus p must be greater than 5, as we've seen before. Let's look at this question. We're going to do tech free, then tech active. Find an approximate 95% confidence interval for the proportion of P primary school children in Australia who regularly use social media if we select a random sample of 20 and find the sample proportion P hat to be 0.7. Notice how this is the same question that, well, the same scenario that I looked at with a point estimate before. We're going to do it with an interval estimate now. So we write down the given information. So we've got P hat equals 0.7, N is 20. And what we do is we chunk the formula into its constituents. Now, one part of the formula is this part here. So we've got P hat outside of 1 minus P hat over N, and then we take the square root, and from that we get 0.7 times 0.3 over 20, which is 0.1025. Now, dealing with a 95% confidence interval, which I'll just call its initials CI, using the rest of the formula, we have 0.7 minus 1.96 times 0.1025, the lower end of the interval, and then the upper end of the interval, 0.7 plus 1.96, because remember this is a 95% confidence interval. If we were doing 99, for example, they'd be, these numbers here would be 2.58, for example, or for 90%, 1.64. Okay, those quantiles have different values for those confidence intervals. And times by 0.1025. Okay, so that comes out, the interval itself is 0.499 to 0.901. And remember, in the next video we're going to interpret what this means, but this video is about being able to calculate it. We're going to interpret these results. Now, we've already explained what a confidence interval is, but there's another video to interpret the results coming your way. So the tech active part. So using a TI Inspire, we go statistics, and then we go confidence intervals. 1 prop Z interval. Option 5 here. Okay, so we were looking at, out of 20, we had a 0.7 sample proportion. 0.7 of 20 is 14. That would mean 14. Okay, so 14 there, and there were a total of 20 as we saw. And we've got, see how the interval's already set at 0.95, the 95% confidence level, so we don't need to change that. These can be changed to other values. Okay, you can enter in other values, but I'm going to leave that there because that's what we want. And you can see that we've got 0.499, and if we round that, 0.901. That's the same answer. Okay, one last one, which is a tech active again. So we have a survey that 237 out of 500 undergraduate university students questioned intended to take a postgrad course in the future. 95% confidence interval is needed here. Okay, so let's find that. So we'll use the tech active again. So we have 237 out of 500. So let's go through that again. So 237 out of 500. And try that again. So we got statistics, confidence intervals, one prop Z interval, and 237 out of 500, and it's already at 95. Alright, so we got 0.430518 written to 3 decimal places. That's the confidence interval for a 95% confidence level. Next video we'll be interpreting this stuff.